Recall what's meant by valence bond theory. Valence bond as opposed to a molecular orbital. These characteristics are true for any compound. The focus, the attempt in either one is trying to explain why atoms bond together and make molecules. Valence bond theory uses the valence electrons in each of the atoms and shares them between the in the space between the atoms. The electrons still belong to each of the atoms. They're only on loan, so to speak, when we form the bond. So if we have something like this, like a dihydrogen, then one electron still belongs to this one and one electron still belongs to that one. We just share it because it's energetically advantageous. Okay. Whereas the molecular orbital model is more like chemical communism, right? It's all the electrons belong to the collective. So the advantages to the valence bond theory is, well, first of all, it came before molecular orbital, but it had some shortcomings, and we're going to talk about those, refresh your memory on those in a minute. The major difference between the two is this theory had no way of predicting energies. So when you put the molecule together, you can't say anything about the energies of the electrons. You can give sort of a qualitative expression like these electrons will be higher in energy than those, but you can't say anything about the absolute energies. Whereas the molecular orbital theory, including the textbook full of equations that go with it, can predict energies. Okay, so let's get to the slides and keep me from wandering. Oh, the other thing that comes with the valence bond theory is an ability to predict structure, three-dimensional structure. Okay, and we use a VSEPR model for that one, valence shell electron pair repulsion. So that's probably still familiar to most of you. Okay, so what can we say about well, let's take this in order. In order to get to this point, we need to be able to draw the Lewis structure, and we know how to do that. Then the VSEPR model is focused on individual central atoms one at a time. So that's not a problem for simple molecules like methane, right? We know that one's tetrahedral. But when you get to huge molecules, like polymers, or even smaller molecules like alkanes, and alkanes wouldn't be a good example, say substituted alkane of some kind. It becomes problematic as the ability of this model to predict the overall geometry of the molecule. You can focus on individual central atoms in the molecule and say, we can predict the structure around that atom. But when you're trying to talk about the entire molecule, then it kind of falls apart. Okay. Okay. The example here is that we can predict that this molecule ethene, and we haven't got to naming. Maybe I should have done the inner chapter B first. Anyway, the ethene molecule, which would be CH2, CH2. So it would look like this. And we could say that the geometry around that one is trigonal planar and the geometry around this one is trigonal planar. And they're both trigonal planar. And we know from experiments that the whole molecule is planar, right? But the theory itself, well, we have to be logical about it. I mean, we can't really hard predict it with, say, math. But if the whole molecule is planar, that means that we cannot rotate around that bond. Right? Double bonds or triple bonds do not rotate. Single bonds, yeah, you can spin them all day long. But the VS-EPR model doesn't predict that for us. We just know it doesn't happen. So that the B part of this picture says, why can't we just turn it 90 degrees and put the hydrogen out here and like that? Say, can't we do this? Right? This other way like that. Why can't we do that? Right? The VS-EPR model can't predict that. We know that single covalent bonds are 2 electrons each. And usually, but not always, 1 electron is donated from one atom and 1 is donated from the other one. Remember what we call it when both electrons come from one side? It's a coordinate covalent bond. Yeah. And that does happen. So the other problem that we have is symmetry. If we're going from atomic orbital models to symmetry problems with the molecule, go from atomic orbitals to how do you get the symmetry, say, for CH4 to be tetrahedral? We know it's tetrahedral, right? Experiments prove it, right? But if we say that it's a 1s2, 2s2, 2p2 for carbon, this is the carbon, and then of course you have each of the hydrogens just 1s1. So you're going to form a single bond with each one of those hydrogens in the carbon. But if we use the valence bond theory, we're going to have 2 of them bonding with the S's here and 2 of them bonding with the P's there. That won't give you tetrahedral symmetry. So what do we do when our theory fails? One option is you modify it, right? You fix it. And the way we fix this one is with hybridization. Remember, now these two go together and we make a sp3 hybrid orbital, and we have 2 from here and 2 from here. So we have 4 of these equivalent orbitals, and that gives us the tetrahedral symmetry. But like I said before, this solves the problem in imagination, right? But it doesn't predict anything about energies. We know that all the bonds are equal in length, equal in strength, and that's as far as it goes. So we also know that if there's a single bond between 2 atoms, it's always a sigma bond. Sigma bonds form on axis between atoms, right? And you have to have at least one you can only have one sigma bond because there's only one axis. Then if you have any more bonds, they have to be sideways overlap of unused p orbitals to give you pi bonds. So you can have 1 sigma and 2 pi bonds maximum. In this case, for our dihydrogen, we only have 1 sigma bond. All single bonds have to be sigmas. I talked about this already, right? This is our fix. Hybridization of the orbitals allows us to produce a tetrahedral structure. Okay, so this hybridization produces, and these are visual models of what we think the orbital space would look like. Remember, when we talk about orbitals, we're not talking about absolute positions in space because of the Heisenberg uncertainty principle. All we can say is this is the most likely, this is the probable space that the electrons would occupy. Because we're more interested in their energies when we can get it. So we minimize the error for the energies, and that maximizes the position problem. Right, so we won't beat that horse anymore. But this is what we think that the hybridization of the s orbital and the p orbital looks like. Right, it gives us space on one side. It gives us more probability on one side than the other for the hybrid orbital. So once we hybridize them, we get these four equivalent orbitals pointing to the apexes of a tetrahedron. Right, and when we consider the relative character, right, does the sp3 orbital look more like a p or like an s? It looks more like a p because we put 3 in. It has like a 75% share of the probability, and s only has a 25% share. So when we say appearance and character, you just look for the ratio of s's and p's. So an sp2 hybrid orbital would be 33% s, 66 or 67% p. And an sp hybrid would be 50-50. Okay, I'm trying to dredge up memories from Chem 101, I think it was, the end of the semester. Okay, so if we do overlap hydrogens and the hybrid orbitals, then we do get the symmetry, the correct symmetry for the methane molecule. So let's see. Hydrogen and chlorine atoms in HCl are held together by a single covalent bond. That's what valence bond theory would predict. What type of symmetry does that bond have? Well, the symmetry would have to be, there's only one atom on one side of the chlorine. It has to be linear. I mean, there's no other choice. So that's what it would look like if we drew the orbitals. Now we don't have to. We don't have to hybridize. We don't have to hybridize the chlorine because we've only got one bond. So we only use hybridization when it's necessary. Let's put it that way. Okay. Now, when we get more complicated molecules, if we have, this is methanol, CH3OH, then we're substituting an alcohol group for a hydrogen on the methane molecule. And if we look at the symmetry around central atoms, and central atoms in this case, we only have two of them, carbon or oxygen. Oxygen would give us it would be like it's a hybridized orbital that gives us a tetrahedral electronic structure or a bent molecule if we ignore the lone pairs. It's kind of like a water molecule in that respect. And around the carbon, we still got that tetrahedral arrangement. But we only have sigma bonds. That's it. The sigma bonds are all that's required to construct this molecule. But we have to put in the lone pairs. if for no other, well, with the valence bond theory, the lone pairs are required to fill out the number of electrons that go into the construction. And they also complete an octet. Right? We do have the possibility for less than or greater than octets, but not with oxygen, nitrogen, carbon, fluorine. We never exceed the octet there. So if you're trying to build a molecule with carbon, nitrogen, oxygen, or fluorine, then you're pretty much focused on fulfilling the octet rule. Now, when you get to boron, it can be less than. When you get to the third period, then we can go greater than octet. But for organic chemistry, we're going to focus on carbon, nitrogen, oxygen primarily, and maybe sulfur. And one or more of the halogens. So we can limit our scope to focus on completing octets. Okay. So, too far. There we go. So, remember what a trigonal planar looks like. It requires what? With 3 required equally spaced bonds around each of the carbons, trigonal planar is required. So we have to hybridize the carbons SPs into sp2s to give 3 equivalents. And that leaves a p left over. Right? So we would have that carbon with its, I'm not going to draw the small lobes. These would each be sp2 hybrid orbitals. See, we have 3 of these, and we put 1, 2, 3 into making them. So we have the same number of hybrid orbitals that come out as the atomic orbitals that go in. And what we have left over is an unused p orbital. Okay, so we have 1 hydrogen over here, a hydrogen over here, and then we can put another carbon over there with its hybrid orbitals. Right, so it overlaps like that. So those are our sp2 orbitals that overlap. That gives you a sigma bond right here. Well, we also have an unused p here. So to complete the octet, we take the electrons that are available in the p orbitals. We have 1 each, and then we form our pi bond like that. Okay, so that gives us the trigonal planar symmetry and the pi bond within the valence bond theory. Okay, and this is a visual representation of what it should look like. Oops. I flipped it too fast. I have to give it time to catch up. Okay. So let's see. These are possible orientations of our sp2 hybrid orbitals. If we're going to get an overlap, we've got to rotate one of those carbon sp2s around so that they can overlap. That's the only way that you can do it. So what we end up with is, let's see, is it on the next slide? Yeah. What we end up with is an arrangement. We have to arrange the sp2 orbitals so that the unused p orbitals are in the same plane. If they're not in the same plane, they can't overlap, right? So that's kind of a partial explanation for why this whole molecule is planar. It has to be planar in order to get that overlap of the p orbitals. So this trigonal planar of this carbon has to be in the same plane as that carbon, so that the unused p orbitals are also in their same plane. Okay, so this is a representation of what a pi orbital looks like, a pi bond looks like. And what you'll notice is that first of all, the distance that's covered by the orbitals in order to make the bond is greater. It kind of spreads the probability out more than it does on axis, which tends to weaken a bond. If you spread out the electrons, then you weaken the bond, or if you shift them to one side or the other, that also weakens a bond, which has to do with one of those questions where we had what was it, carbon versus carbon silicon, was it? Yeah, the polarity of the bond. If the bond is, as it goes more and more polar, weakens the bond because you move more electron density away from the bond itself and toward the atom. So with that in mind, when you try to form a pi bond, the pi bonds do form, and they offer an energetic advantage to the molecule, in addition to completing the octet and all these other little rules that we have to satisfy. There's an energetic advantage to forming the pi bond. But it's not as big an advantage as a sigma bond, because a sigma bond has much more overlap and shortens the distance between the nuclei. Okay. All right. We already said this before. Anytime you have a double bond, it has to be one sigma and one pi. There's no way around that. And that strengthens the bond between the carbons. All right. What happens when if a carbon atom has 3 single bonds and no lone pairs, then what is its formal charge going to be? Let's draw this molecule. And we'll put in all the hydrogens so we can talk about them too. And then we've got a hydrogen out to the back and hydrogen out front. So calculate the formal charge. So the number of valence electrons for this carbon is 4, and we have 1, 2, 3, 4 carbons that belong to it. That's 0. So this formal charge for that carbon is 0. This carbon starts off with 4 as a free atom, but now we only have 1, 2, 3 left over. So that's a +1 formal charge for that carbon. That's why we put that plus there. And with only 3 bonds, and the only 3 bonds are required, this one, while this one would be sp3 hybridized to give you 4 equivalents, this would only be sp2 hybridized to give you 3 equivalent bonds. And then it would have an unused p orbital that does not participate in bonding because it doesn't have an electron to donate. Well, this one doesn't either, right? It's all tied up. So what we've done is essentially we've taken this ethane molecule, right? To get to that point, we've taken that ethane and we've taken that hydrogen away along with both electrons of the bond. And that leaves you with a +1 formal charge and a modification to the hybridization. So remember, hybrid orbitals only form when they're needed. And in this case, if we took that hydrogen away, now we need a different hybrid orbital. Instead of an sp3 before, now we only need an sp2. So for some magical way, the orbital array reconfigures itself into sp2s. See, there's the deeper we get into these anomalies with the valence bond theory, or any theory actually, more magic we have to inject. Okay, so if we have a linear molecule, if we have acetylene, if we have acetylene, now we're going to have a triple bond between the carbons. That means 1 sigma and 2 pi's. And that means carbon typically has 4 bonds, right? Unless it's charged, has 4 bonds. So it has 3 on this side, 1 on that side, 3 on this side, 1 on that side. So that's one, like a way to check yourself. So the hybridization here, it only needs 2 equivalent bonds to make this bond and that bond, sigmas on either side. So it's we have sp hybridization. Actually, 2 sp hybrid orbitals. In order to complete that, that means we have an unused p this direction and 1 going into the board, p that direction. Same thing for this one. So you can get a pi bond for the pi that's in the same plane as this one on this side will overlap, and then the one that's on this side will also overlap, and that'll give you 2 pi bonds. We've probably got a drawing here. Yeah. Let's see. These are the possible orientations of the unused p orbitals. So 1 on the left, we have a p orbital on the y-axis and 1 on the z-axis. And if the other molecule also has a y-axis p and a z-axis p, then we can get the overlap. And this is generally what it would look like if we could get down to be small enough to see it. What was that movie back in the late 60s or 70s? Fantastic Voyage, where the people they had to go find something in this patient, so they shrunk the little ship down, and the people, they shrunk them down like this. That was a Raquel Welch movie, wasn't it? I think it was. They shrunk them all down and injected them into the patient. I still don't think they were small enough to see atoms. I mean, maybe that was, yeah, I think they did. Yeah, I think they did see. The red corpuscles were like big basketballs, and then they could see some atoms here and there. Okay, I digress. All right, so this goes back to the chart. If you remember the chart that I created for valence bond theory and hybridization of orbitals, and I put the number of electron groups on this side, the geometry that it leads to, and the hybridization of the orbitals required, if you remember way back when. So if you need 2 equivalent orbitals, and let's be organic about this. If you need 2 equivalent orbitals around your carbon atom, then you would sp hybridize. If you needed 3, you would sp2 hybridize. If you need 4, you could sp3 hybridize. And that's the limit. Right? That's all the hybridization that we're going to get out of it. Okay. Let's and we haven't even got to the molecular orbital model yet. And even when we do use the molecular orbital model, occasionally we interject valence bond theory into a discussion of a particular molecule because it helps us rationalize the facts. So you're going to see that. For instance, at the end of, was it chapter 9, I think? We were in molecular orbitals. And we talked about the benzene ring and how we could justify molecular orbitals for the benzene ring, but in order to rationalize the bond lengths all being the same, bond strengths all being the same, we interjected delocalization, which is a valence bond corollary. And we had this donut of electron density around top and the bottom, if you remember that picture. So there we sort of we hybridized the two theories. Okay, now to this problem. What's the hybridization of each non-hydrogen atom in this molecule? How many total sigma and pi bonds are there? That's the easy one. Let's do the sigma pi's first. Let's see. We got an oxygen over here, like that, like that. And we got this and a nitrogen. Okay. Now, before we go any further, we may not need this, but it's always instructive to add. Nitrogen typically forms 3 bonds and has 1 lone pair. So I'm going to put the lone pair in, even though it's not drawn. Oxygen tends to form 2 bonds with 2 lone pairs. So I'm going to put those in. These carbons, well, let's see, that's a double bond. This carbon has 2 bonds to it, so that means it's going to have 2 hydrogens with 4 bonds. This one has already 3 bonds, so it's only 1 hydrogen, 2 hydrogens, nothing extra. 1, 2, 3, there's going to be a hydrogen there. This one has 4 bonds around the carbon. It's got nothing else going for it. And this one already has its octet, so there's no hydrogens there. Okay. Just so that we understand what that drawing means. Okay, let's count the sigma and pi bonds. That's the easy part. Right? We're going to have, there's a carbon here, so we're going to have a sigma. We have 1, 2, 3, 4, 5, 6, 7 for the carbons. Then for the hydrogens, we're going to come down here with 1 hydrogen there. We have 2 here. These are sigma bonds. We're going to have 1 there and 1 there, so that's 2 more. We're going to have 2 here. So 2, 4, 6, 7, 14. We're going to have 14 sigma bonds in that molecule. Okay, pi bonds. You're never going to have a pi bond with a hydrogen atom. Right? It will not happen. So pi bonds, we're going to have 1 there and 2 here. So that's 3 pi's. Okay. So we got that question done. Now, what's the hybridization of each of the non-hydrogen atoms? Well, let's start from this side. Non-hydrogens. This nitrogen needs some place for both the bonding side and the lone pairs to go. So this is a linear electronic arrangement, which means it's sp hybridized. And it has 2 unused p orbitals, 1 for this pi bond and 1 for that pi bond. The same thing for this carbon. It's sp hybridized because it has 1 on one side and 1 on the other, and it needs a pi bond, p orbital for that pi and a p orbital for that pi. Okay. This one has 1, 2, 3, 4 attached to that carbon. So that's sp3. This is also sp3. This one has 1, 2, and this hydrogen makes it sp2 hybridized. sp2 on this one. This one has 4 bonds. It's sp3. And this one needs, since it has no double bonds, then we're going to hybridize everything. So this oxygen, let's see. Let me think about it. Do we need to hybridize that oxygen? Well, if we have 1, 2, 3, 4 groups to that oxygen, it's got to be tetrahedral, which means it's got to be sp3 hybridized. Okay, Now let's see how many of these I got wrong and how many I got right. Okay, let's see. Well, we did the total first, so we'll have to come to that afterwards. Excuse me. SP hybridized, I'm going from the right, moving in. Yep. Excuse me. SP3, yep. SP3, yes. SP2, and SP3. So we got the hybridizations correct. And then we're starting to count in that bottom frame. We're starting to count the sigmas and the pi's. So let's just look at the total and see. Wait a minute. What is the total? Is it not going to tell us? Or did I read it wrong? How many? Yeah, how many? It doesn't give us an answer. I'm missing a slide, I think. I'm missing a slide. What types of bonds? Okay, how many single, double, triple bonds are there in the molecule? All right. Thank you, Mark. Oh, yeah, I'm right. Okay. I mowed the grass yesterday under dry conditions, and the sun was kind of low, and you could see like the particulates floating in the air, and I was sucking it into my lungs. And I'm still paying for it today. Okay, let's talk about bond rotations. We know from physical evidence that sigma bonds are free to rotate. So anytime you have a sigma bond, anything attached to that sigma bond can rotate in continuous positions. Now, they may prefer or spend more time in one position than other, and we'll talk about that also when we get to Newman projections. They help us visualize things around rotatable bonds. But for this one, ethane, any position is, well, no, I can't say that either. Let's just say for now it rotates around single bonds. Double bonds, it can't rotate because those pi bonds have to be in the same plane in order to overlap. And if you twist this side out like that, you're going to break that bond. Now that can happen, right? If you add enough energy to ethene, then you can put so much strain on that bond that it will break. But under normal conditions, like 1 atmosphere pressure and room temperature is not going to do that. That's extreme position. And if you want to break the bond, then you got to really want to do it. Okay. So this is an attempt to explain, why it happens. The top one is rotating around the carbon-carbon bond because it's a single bond. And we can't rotate around the one with the pi bond because it puts the p orbitals out of the line. That's the simplest explanation. So what we've outlined here in this molecule, and we're not going to try to name that one because it's got a double bond in it and we haven't covered that yet. But for illustration purposes, we know that, excuse me, those 1, 2, 3, 4, 5 carbons are all in the same plane. They have to be in the same plane because those 2 central carbons with the pi bond are sp2 hybridized. That means trigonal planar. And trigonal planar is planar, it's flat. Okay. Okay, we're going to get into a little naming convention here. It's starting to look like I should have done interchapter B first. But it's too late now. I'm too deep into this. If we name this compound, let's say we try to name this compound. Say it's this one here, and we're going to put the chlorines on this side and hydrogens on this side. We start with the aliphatic hydrocarbon. The longest carbon chain here is 2. So that would be starting as ethane, right? But it's got a double bond. So we just change this one, ethene. Now that is the central part of the molecules, ethene. Now we need to attach some things to it. We only have to identify the chlorines. So it's going to be a dichloro. But we have to say where they are. They're on the 1 and the 2 carbon. Okay, so that's the name for that one. Now, if we put the chlorine down here, right, instead of up there, well, in this position, this molecule is in what's called the cis position, where you have the chlorines on the same side of the double bond. So that's cis. If we move the chlorine down here, like this, that's the trans orientation. This part of the molecule is named exactly the same because they're still attached to the same carbon. And the evidence for that is boiling point. Right? We find the higher boiling point with the chlorines on one side of the carbons. What that does is it concentrates with these. This would be a polar bond, right? And these kind of pull opposite one another. But if it's on the same side, then we give it a molecular polarity that's more like this, if it's cis. And that would increase its boiling point. Now, this is still used in common language, but this naming convention we would call trivial because the standard is different. And hopefully I'll get to that in Interchapter B. Okay, does this molecule have 2 distinct configurations about the double bond? Does this molecule have 2? Well, I can imagine, right? If we leave the methyl group where it is and move the chlorine from the bottom up to where hydrogen is, swap places, because we can't rotate the bond. Can't do that. So we could theoretically move the chlorine to the hydrogen position in opposite, and instead of the trans dichloro, we would have a cis dichloro. Let's see. Yes. So to answer the question, yes, you can have 2 distinct configurations. And when you change configurations like that, we're talking about isomers. Right? And these are organic isomers, right? Not atomic isomers. That's a different concept. Okay. You can have, if the molecule is really long, particularly for things like fatty acids, you can have multiple double bonds. And in this case, for alpha linolenic acid, and this is naturally occurring fatty acids, always have cis. Wherever there's a double bond, it's the cis orientation. If you modify them chemically yourself, it always ends up trans. And when they say trans fats are bad for you, it's because they don't react the same way as cis fats do. So cis fatty acids or fats from natural sources are metabolically better for you. Okay, so we have this series of double bonds, right? Notice they're spaced. There's a carbon in between each double bonded carbon. So that separates them, that separates their electron density away from each one of those carbons, single bonded carbons in the middle. Right? That makes them behave independently from one another. We're going to get into a discussion later, I hope, called conjugation. And if you have the double bonds in neighboring carbons, right, if we move this double bond down here, then it would conjugate and they would interact and you get a completely different animal altogether. But that's for another time. But this cis orientation says that the hydrogens are on one side and the other moieties of the molecule are on the same side. Okay, we could get our model kit out, but I don't think it would add to our discussion. This slide doesn't add much either. So let's move on. Oh, this whole discussion is about modeling kits. All right. If we drew this molecule, right, so it would have three, if we started with those three carbons, right, and there's a double bond on both sides. So that carbon's got its octet, and these would have their hydrogens. I'm not going to go into naming that because we haven't covered the rules yet. But you'll notice that the double bond on one side of the carbon is different than the double on the other side. It's rotated 90 degrees, and that's simply for overlapping the unused p orbitals. Okay, let's see. As we go from sp3, sp2 to sp, the bonds become shorter and stronger. The reason for that is not because of the hybridization itself, but because of the leftover p orbitals that overlap and form the pi orbitals. And the pi orbitals draw the atoms together. We strengthen the bond and we draw them closer together, but notice that the strength of the bond is not linear. We do decrease the length of the bond. Let's see. No, that top one with the blues and the reds, those are talking about the hydrogens. Okay, I was referencing the carbons. The carbon-hydrogen bonds also decrease in length as we change the hybridization from sp3 to sp to sp2. And we can trace that difference, that shrinking of the distance between the hydrogens in each successive molecule. We can trace that to the sp character. Right? If we have more p character, then we tend to extend the hybrid orbital out more. If we have more s character, then it's more spherical and it draws it in. So the overlap occurs closer to the carbon atom. Okay. All right, moving on. Well, that's what we're saying right here. I stole my own thunder. Actually, I stole the PowerPoint thunder. That's all we're saying is as we add more S character, we draw the bond in closer to the carbon atom. And when the hydrogen bonds to it, it has to get closer to the carbon, shortens the bond. Okay. There's also an effect of electronegativity. As we hybridize the central atom, its effective electronegativity increases. So one way to look at that is the number of hydrogen atoms attached to each carbon. If we have more than one hydrogen attached, then the more hydrogens you have attached and the more p character you have you tend to have more room for your electrons, right? They can smear over 3 hydrogens instead of 2. Plus, and this, I think this is more important. Once we start forming pi bonds, that concentrates electron density in between the atoms, right? Sigma bonds, definitely, they're on axis. The electrons are on axis. But if we draw electrons that would have been used for those hydrogens, those extra hydrogens, now we only got 2 hydrogens out there, and the electrons that would have been used there are now drawn into the center. So that puts the effective electronegativity for a pi bonded molecule between the carbons. So as we increase the number of pi bonds, we also increase the effective electronegativity of that space between the carbon atoms. Okay, so in which molecule, A or B, do you think the carbon double bond distance are longer? And in which molecule are the carbon-carbon bonds stronger? Okay, longer means weaker, shorter means stronger. Okay, so I would expect that the carbon-carbon double bonds would be stronger for B, shorter and stronger for B. So what's the hybridization of each of the atoms involved? Well, the hybridizations for the on the left one, for the 1, 2, and the 4, 5 carbons, those would have to be sp2 hybridized. The carbon in the middle on the B side would be sp hybridized. Okay, and that's what we're saying right here in this solution. And then what is the S character of each of these carbon atoms? Well, the S character for the A's, the hybrid orbitals on the A's, is less pronounced. So that moves the carbons further apart. And for that carbon in the middle, for the B, that's sp hybridized. It draws those other carbons together closer in order to make the overlap. So the answer is B would have the shorter and stronger bonds. Okay. Remember our discussion of light sometimes behaves like a wave and sometimes like a particle. Okay. Well, you can say the same thing about matter. Sometimes matter behaves like a wave and sometimes it behaves like a particle. And when we're talking about bonding, we're talking about electrons. So electrons can be seen as either particles or as waves. And if we look at them as waves, then we have to consider interference, constructive and destructive interference, in order to fully understand how electrons behave. And the Schrodinger equations, well, for both free atoms and for bonded atoms, introduces this factor, this wave function variable, which is called psi. Right? It looks like a pitchfork. And it expresses the, well, it's central to the discussion of the wave nature of electrons. The amplitude of the electron's wave function is similar to the displacement of the hump on that rope. Like we take a rope and do like that. I used to do that for my high school students. I taught 1 year and that was enough. But I would take this, I had this long spring. It was a fairly stiff spring. And I'd attach it to the door on one side and then I'd do like that. And then see the wave travel down and back, down and back. And And so that's what we're doing with this rope. We can either displace it to the positive side or to the negative side. And now we need to talk about interference. Where are we going with this? Okay, so we're trying to take that concept of wave nature and the amplitude of the wave and bring it over to a three-dimensional wave understanding of electrons and how this affects their bonding. So we're heading toward molecular orbitals. When you're talking about wave functions, then you're dipping your toes in molecular orbital pool now. And in that equation, this psi function is going to be squared because the psi itself says something about amplitude, but it doesn't really tell us anything about how the electron is behaving or where it is. And if we square it, as it does in the equation itself, the Schrodinger equation, now we're talking that function is related to, proportional to the probability of finding an electron someplace. So that's the part of the equation we use to map out the spherical or the dumbbell shape and those different shapes. Okay. We say that if we have this 1s orbital, it's going to be spherical, right? And it's going to, this representation tells us it's a 90% probability that the electron will be found there. That doesn't mean it will always be there. And I can see the confusion that can develop over, if we were talking about waves, electrons as waves, now we're talking about electrons as particles. Because if you're talking about where is the electron, you have to think in terms of particle. Right? So we're mixing those two concepts at the same time. But the probability itself can be a wave expression. I like to look at it this way. If we take simple atom, like any atom with its nucleus, and we have an orbital out here. In the Bohr model, the electron was like a planet, right, going around the nucleus. Well, that didn't work because what's this electron doing as it goes around? Changing directions. And we know that anytime something changes directions, it has to give up energy. So eventually it would go crash into the nucleus. Doesn't do that, right? So that's where the Bohr model fails. So instead of that concept, if we think of the electron as a wave, at that probability distance from the nucleus, and there's the orbital, right? Now we can keep it out there and it doesn't have to crash into the nucleus if the electron is more like a wave. Well, we can take this concept and extend it to bonding orbitals, right? Which is where we're headed with molecular orbitals. Bonding versus anti-bonding. The bonding orbitals have a probability of finding the electron some space between the nuclei. Okay? Anti-bonding orbitals put a node between the atoms. A place where you have zero probability of finding an electron there. So that's why they call it anti-bonding, because it doesn't contribute to the bonding, it detracts from the bonding. Excuse me. Now, whenever you have, remember that rope, it went along and then had a hump this way, or it went along and had a hump this way. Those are two different ropes. You can think of those as one way is one phase, the other way is the other phase. And they can exist at the same time in this three-dimensional space. Right? Now I'm really trying to twist your head around backwards. But that's the way the orbitals, the probability function is expressed in terms of phases. We can have a phase on one side or phase on the other side. Now, if we have two, now we're going to talk about interference. Okay, still remember basic ideas about interference. Right? If two waves approach each other, this is our simplest explanation. We got a hump, a wave moving in from this side and one from this side. And when they meet, they're the same amplitude and they have the same wavelength. Right? So when they meet, they constructively interfere. They add to each other. And then they go on the other side as if nothing ever happened. If the phase on one is negative and the phase on the other one's positive, when they meet, then they destructively interfere. And it's like they disappear for an instant before they reemerge and go on their way. Now, the one on the left is easy for me to wrap my mind around, but the one on the right is just completely off the wall. I mean, if it's destroyed, it shouldn't come back, but it does. Okay. So in terms of bonding, if we have a bond formed between two atoms, like like hydrogen atoms, and we have this 1s orbital overlapping this 1s orbital, we form the sigma bond because the phases match between the hydrogens. These phases constructively interfere. This region of space that's assigned to that orbital constructively interferes, and it increases the probability of finding an electron there. So the chi-square function increases for this region, and it decreases for this region. So before, the hydrogen atom had its chi-squared function. Each one had their chi-square, but now after the bond forms, there's a chi-square for the molecule. And it says that the probability is going to be focused right here between the atoms. There'll be a slight probability out here, but most of it will be between. Now, if we have out of phase, if one is one phase and the other is opposite phase, then we get the probability of finding electron out here and out here. And that's your anti-bonding orbital. And notice that it does not contribute. And if you recall, when we drew the molecular orbital model, we had the 1s, this is energy. We had the 1s from this hydrogen and the 1s from this hydrogen, and they go together to form, start with 2, we end with 2. Right? So this is the sigma from the 1s, and this is the sigma star from the 1s. This one is representation of constructive interference. This one is destructive interference. Right? Well, if we only have one electron from each and we follow the Aufbau principle, then we fill from lowest energy to high. Both of these go in this orbital. So we don't have any electrons in the anti-bonding. And if we calculate the bond order, remember, it's 2 minus 0 divided by 2 equals 1, which is a single bond. All right. So let's see, let's make some room here. We're going to stick with the molecular orbital model now. And add a concept. We're trying to simplify things because molecular molecules, not organic molecules, can be unwieldy, especially if you're trying to construct molecular orbital energy diagram for those. It can be done, but we don't need to do it. because we have simplified procedures for understanding how these bonds form. Okay, so molecular orbitals are MOs, atomic orbitals are AOs, and when you form the molecular orbitals, all the atoms that go into the molecule contribute their atomic orbitals and they disappear. They come out the other side as an array of molecular orbitals. With certain exceptions. If the atomic orbitals are not being used in the bonding process, initially, when the molecular orbitals are formed, they remain as atomic orbitals. So that's where we had the bonds formed, and then before the pi bonds formed, we had these extra p orbitals. Those are atomic orbitals, but we overlap them, and now we form the pi bonds, and they go into the mix as well. So we use this concept. Actually, it's an algorithm for calculating what the nature of each molecular orbital is, the linear combination of atomic orbitals. When I think of linear combinations, I think of A plus B plus C plus D, right? And that's a common procedure, a common technique in the sciences. Statistics uses it all the time. And it works. That's why we keep using it. So we've already said this, the number of molecular orbitals is the same number as the atomic orbitals that contribute to. There's a conservation principle here. We'll come back to this linear combination in a minute. But I've already shown you the diagram for this one. You have two possibilities. You can have a bonding molecular orbital or an anti-bonding molecular orbital. And we form a node between the hydrogens. So that psi square function tells us that there's no electron density expected between the hydrogens for the anti-bonding orbital. But since we don't have any electrons in it, we can calculate the bond order, but otherwise we don't have to consider it unless you change the number of electrons. Right? If we add an electron to an H2 molecule and made it a negative charge, it would decrease the bond order to 1/2. Or if we couldn't remove an electron, we wouldn't have a bond. Okay, so that's what we were talking about before. Bonding molecular orbital. Now for hydrogen, and we also say, what is the highest occupied molecular orbital? Right? For the dihydrogen molecule, the highest occupied, or the HOMO, molecular orbital is the sigma formed from the 1s. The lowest unoccupied molecular orbital, and this is in terms of energy. So the lowest unoccupied would be the nearest one in energy to the highest occupied. Okay, that's always the case. And this one would be the antibonding. This one is occupied with 2 electrons. That one has no electrons. Okay. We can also get non-bonding molecular orbitals, which have about the same energy as the atomic orbitals from which they form. That's one thing that we didn't spend a whole lot of time on in general chemistry. And main reason is we didn't have time. But the other reason is it wasn't important for understanding the basic principles of molecular orbital theory. But they do exist, the non-bonding molecular orbitals. Okay, let's see. So it looks to me like we're trying to hybridize the hybrid orbitals with the molecular orbital theory. And the only reason that we're throwing this confusing concept at you is because it's useful. We're only going to consider, well, first of all, remember when we were talking about in general chemistry, we were talking about molecular orbitals. We usually only considered the valence shells. The molecular orbitals formed from the valence electrons. Because the core, in either theory, the cores don't participate. Well, in valence bond theory, definitely the cores don't participate. But in molecular orbitals, they're not important because the valence electrons forming molecular orbitals incorporate the HOMO and the LUMO. Okay, and that's where we're going to focus our attention. So we'll continue that in this organic understanding. Now we can form molecular orbitals from hybridized atomic orbitals, and that can be useful also. So if we have these two, excuse me, if we have these two, oh, I dropped my cap. There it is. In this example, what we're trying to do is we're combining, looks like a 1s orbital with a hybridized, does it tell us which one it is? It doesn't. Consists of sp2, sp2, and sp3 consists of one large lobe. So we're sort of generalizing. So this could be an sp or sp2 or sp3. And then the red one is simply an s orbital. So if we hybridize if we form a molecular orbital from a hybrid orbital and a non-hybridized orbital, then we can get a certain type of molecular orbital. But we're still going to get two molecular orbitals out of the two atomic orbitals. We'll get a different electron density arrangement if we try to overlap the same type, say an sp2 and an sp2. Right? And that gives us a different probabilities shown in the green on the bottom. If we look at the one on the bottom left, we see that that type of molecular orbital formation from a hybrid and a non-hybridized orbital, we tend to get a molecular orbital that pushes the electron density toward the S character. Whereas if we hybridize equal components, we get an even distribution in the middle. I think that's the focus here. And we still get the anti-bonding orbital. It's got that node in the middle. So that hasn't changed either. Okay. All right. If we overlap atomic orbitals, the sigmas are fairly easy to understand. Hopefully the pi's won't be that much different, except that when we try to represent their probabilities of electron density, we find that the pi bond molecular orbitals are slightly off axis, and the anti-bonding pi orbitals are it looks like I don't know what you call that. You know what that looks like? That looks like placement of TENS electrodes on my wife's neck. But we have this node in the middle, and then we have the nuclei. You see the little dots there, the nuclei, and it looks like we've identified one node. Well, that plane of no density is the same for both of them between the on axis with the nuclei. On axis with the nuclei, you don't get any density because these are pi molecular orbitals, just like any other representation of pi orbitals. Okay. So we're giving this thing a name. It's called the molecular orbital valence bond model. we're hybridizing two theories. And the only reason we're doing this is because it helps us solve problems. That's the only reason that we would do it. If it doesn't help us solve problems, then there's no reason to introduce this complexity. Excuse me. So let's count how many molecular orbitals are required for this particular ethane molecule. Well, how many bonds do we have? 1, 2, 3, 4, 5, 6, 7. We have 7 molecular orbitals that are in phase or overlap along the axes between the atoms. So we can count those as 7 sigma molecular orbitals because we're not representing any pi bonds in here. Right? So and if you look at the dash wedge representation, there are no pi bonds up there. So if we're going to have 7 sigma bonds, 7 bonding sigmas, we have to have 7 anti-bonding sigmas. So there are 14 molecular orbitals. 14 atomic orbitals go in, 14 molecular orbitals come out. If we step it up and put a pi bond in there and make ethene instead of ethane, now we have how many atomic orbitals? Well, if we count just the sigmas, then we have 1, 2, 3, 4, 5, 6. We have 6 sigma molecular orbitals. And we have 6 anti-bonding molecular orbitals. Why does it say 5? 1, 2, 3, 4. Oh, I'm sorry, 5. I was counting the pi bond, sorry. So we have 5 sigmas. We have 5 sigma bonding and 5 sigma anti-bonding. Then at a little bit higher energy, remember the pi bonds are a little higher in energy because they've got to stretch more. They don't get as good an overlap. So how many pi's do we have? We have 1 pi molecular orbital. So that means we have to have 1 pi anti-bonding molecular orbital. Okay. Now we haven't positioned all of those molecular orbitals. We sort of relatively put them in. We say those 5 sigma molecular orbitals are roughly the same energy. Now we don't know that for sure. Not from this diagram, we can't tell that. But it's safe to say that they're close in energy. The electrons that, if we put the electrons in the bonding orbitals, so let's do that. How many valence electrons do we have? 1, 2, 3, 4. And then each carbon has 4. So that's 8 and 4 is 12. 12 electrons, right? Valence electrons. Okay, so that's what we're looking at here, only the valence. Because we're hybridizing the molecular orbital with valence bond theory, we're sticking with the valence electrons. So if we have 12 electrons, how would they fit in there? Well, the 5 sigma molecular orbitals would take 10 electrons, right? 2 for each one. So that would be, right, we have 2 electrons left over. Where would they go? The 1 pi bonding orbital would have those 2 electrons. And there would be no antibodies. Right? So if we calculated the bond order for this whole molecule, it would simply be 12 minus 0 divided by 2, its bond order would be 6. Right? Now the bond order for a whole molecule like that doesn't make any sense. There's no direct correlation between 6 and single, double, triple bond, unless you parse it out. Then it makes sense. Okay. All right. These are observations. Sigma molecular orbitals are lower in energy than pi molecular orbitals most often. Right. We had situations where when we drew the molecular orbitals for atoms, we had sp mixing, right? And that would flip. Put the pi underneath the sigma. But we're not going there. Right? We're staying simpler. The sigma molecular orbitals are typically higher in energy than the pi star. The sigma star higher than the pi star. So we get sigma, pi molecular orbitals, then pi star, sigma, pi star, and sigma star in relative energies. Okay. So what do we mean by, well, there it is in print. A degenerate orbital is, if you have 2 or more degenerate orbitals, they're the same energy. So in affine, we have 2 degenerate pi molecular orbitals. So instead of, if we have like that, now we're going to drop one of these hydrogens from each side and put a triple bond in there. Affine is the proper name for acetylene. Okay, in this case now, we have how many sigmas? Well, instead of 5 before, now we have 3 molecular orbitals, 3 sigma molecular orbitals, 3 sigma star molecular orbitals. We have 2 pi molecular orbitals and 2 pi star molecular orbitals. Okay, and that's 10 atomic. 10 atomic orbitals go in to make 10 molecular orbitals. So 3, 4, 5, and 5 mirrored to be 10. That's right. Now, how would we use this molecule if we wanted to say, instead of drawing that whole diagram, and the question is how many molecular orbitals are in this molecule, we would say 1, 2, 3, 4, 5 would be the bonding orbitals, double it would add the antibonding. So there'd be 10 molecular orbitals, right? If a question like that popped up on a standard test. Okay, now we're going to complicate the story. And instead of having a symmetrical molecule, we're going to introduce a molecule with lone pairs in it. So that oxygen has 2 lone pairs. We need some place to put those. Since they're not bonding, right, they're not contributing to a sigma or a pi bond of any kind, then they are roughly at the same energy they were when they started. So that's where we can put them into non-bonding molecular orbitals, right? Because we have to conserve orbitals, and we need atomic orbitals for those lone pairs. So when we put them into the molecule, we've got to make molecular orbitals. So how many molecular orbitals will we have in that molecule? Well, if we have like this, let's see if my theory works. We have 1, 2, 3, 4, 5 sigma molecular orbitals and 5 antibonding molecular orbitals. Right? And then we have 2 lone pairs. So each one of these has its own molecular orbital. So we would have 2 plus 10 is 12. I can still do math. Gotta stop and think for a second. Okay. So that gives us a rationale for creating non-bonding molecular orbitals. Oh, that's it. Goody goody. I was afraid I was going to have to stretch my brain more. Just hang on to that concept of LUMO and HOMO. That one will come back. All right, we did that already, and we did this one just now. Y'all need to take a break. Let's talk about naming alkenes, alkynes, and benzene derivatives. In order to name an alkene, we start with the alkane, and we've got examples of that. So we're still looking for the longest chain, but we want the longest chain that incorporates the double or the triple bond. Okay. So in the case of alkenes and alkynes, that might be a shorter chain than you would expect. So in this first one, we've got what? In that colored section, we've got 1, 2, 3, 4, 5. 1, 2, 3, 5 carbons. If we ignored the double bond, we'd have 1, 2, 3, 4, 5, 6 would be the longest carbon chain. But the longest one that incorporates the double bond is only 5. So 5, we would start with pentane, and now it would be pentene, would be the base of the molecule. And then we would start numbering with the lowest number that incorporates the double bond. So we would start at the left-hand side at the top of that double bond. That would be 1, 2. And this would be 2 ethyl. Yeah, we don't do that, do we? 2 ethyl pentene would be that first one. Okay. In order to incorporate cyclic compounds, we have a similar rule. If the cyclic part has a double or a triple bond in it, I can't imagine a triple bond in a cycle. I guess they could have it. Then we're restricted to that cyclobutene is now our base. And we want to number the carbons so that the functional group that's added to it is the lowest possible number. Right? So we would I think I got this right. We would start at that upper left-hand corner. That would be 1, and then 2 would incorporate 1, 2, 3, 4, 5 would be the pentyl, 5-pentyl butene. I could be wrong with that one. Right. I think I'm right. Unless the only thing that would change it is if we had the number 1 would be down the lower left. So the 1, 2 would incorporate the double bond, and then 3 would be the other one. Let's keep going. Okay, for this chain, the first one, we would start numbering from the left because that gives us the lowest number for the double bond. And the chlorine would be at the 5 position. How about the middle one here? We would start from the right-hand side because the side group is a methyl. And if we started at the other end, we'd still get a 3 for our hexene, we still get a 3, but that would make the side group would be at a much higher number. So we start from the other side and say 1, 2, and that would be the 2-methyl 3-hexene. Or maybe they might be putting the 3 in front of the ene. Yeah. The last one is a cyclic compound. And of course, we have included the base molecule is the one with the double bond in it. Okay. For an acyclic alkene or alkyne, we identify the lower of the 2 locator numbers for the double and triple bond and insert it before the ene. Okay, so this would be, where is the ene in this one? Let's go back. Where is that ene located? It's on the, it's 1. Oh, if it's 1, I think that's what that second statement is. If it's 1, that's for a ring compound. So it'd be 2-methyl pent 1-ene. We're saying, where does the double bond start in this pentene chain? Oops, skip one. Okay. And then you add prefixes. All right, let's try this one. What would be the longest chain incorporating the double bond? Well, yeah. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. Yeah, you would go to the left, right? Right, left. And that would so that would be hexene, right? So it'd be hex. Draw the rag. X2 ene. Okay, would be and we would number 1, 2, and at the 3 position would be it would be ethyl, but it would be 1-methyl ethyl. 1-methyl. 1-methyl ethyl. Right? Like this. Would be at the 1, 2, 3 position. It would be 3, 1-methyl ethyl. But we don't know where to put it yet because we haven't got our alphabeticals together. So at 1, 2, 3, 4 would be dichloro. Be 4 dichloro. So C comes before, we don't consider this part. C comes before M, so this would be first. So this would be 4 dichloro, 3 1 methyl ethyl. X2E, I think. Let's see if I got it right. Okay. All right, there's the longest chain. Got that right. The lower of the 2 numbers is 2 is added to the root mean for the en. Okay, so it's hex 2e. We got that part right here. 1-methyl ethyl comes here, and it's at the 3 position. Oh, I forgot the 4-4 because we got 2 of them. Okay. I would have missed that one on my own test. 4,4 dichloro. Now, sometimes it may seem redundant to say 4,4 and then dichloro. Why don't we just say 4,4 chloro? That means we've got to have 2 of them, right? But I think the reasoning is that it's not always 4-4. It could be 3-4. It could be 1-4. It could be 4-5. Who knows? So in order to avoid confusion, we have to incorporate both of them. Okay. What do we do if we've got multiple bonds, multiple double or triple bonds, or a combination? Well, as usual, we establish the root, right? Which one incorporates all of the available double and triple bonds, right? So that first one at the bottom is going to have 1, 2, 3, 4, 5 carbons. Okay, so that's our longest chain. The one in the middle is a cyclic, so we incorporate that cyclohex central atom, and the one on the far right we include starting from the right hand side so that we can make the smallest number for each. Then we have all those triple bonds incorporated. Now notice when we have more than one, we say diene or triene or however many, right? And then we also have to say, where are those located? Right. So if we're going to make the smallest number for the first one on the left, if we started from the end, we'd have 1, 4 diene, right? So that's neither here nor there, except that when we start to add the side group, it needs to be the lowest number also. So that's why we start at the top instead of the far right, to make that 2-propyl penta. Well, the penta is part of the root molecule. 2-propyl occurring at the 2 rather than at the 4. Okay. That was fairly straightforward. And then we say 1,4-diene. For the other one, we want to minimize the number for the side group also. That's a methoxy, right? And it's attached at the number 2 position because we're gonna minimize the numbering system. So 1, 2 would give you a 2 side group rather than 1, 2, 3 side group if we went clockwise instead of counterclockwise. And then 1,3-diene for the cyclohexa, 1,3-diene. For the far right, we want to we want to start numbering with the first carbon that's included in the multiple bonds. So we don't have any choice there. We have to start at the right-hand side at 1. 1 with this ine. So 1, 3, 5. So 1,3,5 triene is part of our 7-carbon chain. So it's hepta 1,3,5 triene. And that means that the 7,7 difluoro goes at that far end. There's no choice there. We can't start at 1 on the left-hand side because that doesn't incorporate the triple bond. Okay. And that would put us at 2, 4, 6 instead of 1,3,5. Okay. Oh, here's a nice one. Name this one. Okay. We want the longest chain that incorporates all of the multiple bonds. So we could either start at the top or the right, just to be sure we have 1, 2, 3, 4, 5, 6, 7. So this is hept. And then we have 1, 2, 3 enes. So that's a triene. Now we need to say, what position are they? Well, if we start from the right, numbering 1, that doesn't incorporate the first triple. So we got to start at the top. So we've got a double bond at 1, 3, and what? 5? 1, 3, 5. Okay. Triene. Now we've got our side groups. So we've got an ethyl group at 2 ethyl. We've got a 1, 2, 3 propyl at 3. And we've got a nitro at 6, right? 6 nitro. Okay. Alphabetical. This one, that one, then this one. So it'd be 2 ethyl, 6 nitro, 3 propyl. CHEM211 triene, I think. Let's see. 2 ethyl, 6 nitro, 3 propyl, CHEM211 triene. Got it.
Instance, it's just crazy.
Yeah, and this is a common tactic in education. Make you do it the hard way first, so that when you get machines to do it for you, you understand what they're doing. So this molecule, if you wanted to name this, then you would create a molecular formula and Google it, or you go into one of these chemistry programs and ask it what the possible names could be. Okay, naming E9s. Now we've got a mixture of double and triples. Okay, so the root is again going to be the longest one that incorporates both of them, both types. But the ending is going to be, ine is going to be the last. We're going to say where the ine is, and then the ene comes before that. I think it's alphabetical. Now, which direction do we number them from? Well, they have equal priority, and the tiebreaker is the ene group. If there's a tie, then we go to the ene. So that's why on the bottom one, instead of, well, actually, that's not really a tie, because in order to have that hex, that 6-carbon chain, we have to start numbering 1 on the left in order to incorporate the first double bond. It's not really a tie. We couldn't start at 6 because there's no double or triple bond attached to 6. So that's not a tiebreaker.
So if there is a triple at 6 and a double at 1,
You
then
still sort of
you would start at the double.
Yes, right. Right. It's the tiebreaker. Yeah. Now the second one, we have to start with 1 with the ine, because it's the first one that has a multiple bond. Okay. But when we name it, we still put the ine on the end and the ene inboard from that. The last one, let's see, how messed up is that one? In a cyclic compound, you would have to start with one of the enes, and you would have to number it so that you would have the lowest numbering system, which really doesn't matter. If you start where it does now and go clockwise, then you get a numbering system. If you start with the 4 and go counterclockwise, you get the same numbering system. Right. So there's no big deal with that one. Okay. Um, let's see. We're not going to have any examples for those. Well, except the ones that are given. Excuse me. Okay. Um, benzenes. When we have a benzene molecule, it's always that 6-carbon ring. And we can either represent it with single double bonds, understanding that benzene has all those bonds are equal. So that's why sometimes we write it like that. All the electrons are delocalized among the atoms of the ring. And this makes benzene a very special kind of group called aromatic. Aromatic comes from the aroma that they put off. A lot of the smelly compounds that you get in perfumes and other maybe natural sources, right, plants and flowers, are based on aromatics. Now, they may not be benzene aromatics. That's where I think we wouldn't get into that until the second semester, where we actually go into aromatics in earnest and decide how to determine if a ring is aromatic or not aromatic, because aromatics have special characteristics and non-aromatics are not part of that special group. But as far as naming compounds goes, you look for this benzene ring. And there are sometimes we're going to have to look at the rules and see. Sometimes the benzene forms the core molecule. And then you substitute on that benzene. And that's where we're starting with this. But sometimes you get the core molecule is not the benzene ring. And then you have to name that benzene as a side group. Right, so we'll get to that one in a minute. But if we establish benzene as the root, then we have to say what's attached to it, and then give the lowest locator number that for the successive substituents, and then add prefixes. So let's look at an example here. All right, so we got this one, and then we're going to put the nitro up here and the chloro here. Okay. So, got the ethyl group. Okay. So we want to number this in such a way the root, of course, is assigned as benzene. Okay. Then we've got 3 side groups, a chloro, a nitro, and an ethyl. So where should the number 1 start? We want to encounter, right. We want to position 1 in such a way that the next one is the closest to it. So that's why we can start here and go clockwise. If we started here, then we have to go to 2 to get to that one. And that would make this one 4. And the numbering system would be larger numbers. But in a ring structure, we're looking for how do you get to the nearest 1? So that would be 1, 2. That's the only way that makes sense. So we've got 1 chloro and a 2 nitro and a 4 ethyl. Now they should still be alphabetical. So C, E, N, right? So it'd be 1 chloro, 4 ethyl, and 2 nitro. benzene. Okay. Now you're going to see this is a trivial naming system, but it's still used extensively. I'm going to leave that up there as illustration. Well, actually, I can't do that because this naming convention only works if you have two substituents. Now, if we have these two substituents, then we can say 1-chloro, 2-nitro. Right, that would be the name for this one. 1-chloro, 2-nitrobenzene. But we could also say the chloro and the nitro are ortho to each other. Ortho, I don't know, taking statistics, ortho means straight. Right? If we can go straight from here to there, right? Only one carbon jump. That's what that is. This is ortho, chloro, nitro, benzene.
So will you expect us to name it like that, or is it still okay to say?
Well, the IUPAC name is 1-chloro, 2-nitrobenzene. That's the proper IUPAC. But I want you to understand how to name it this way also. And in order to get this name, I would have to say, use this convention. If we move, let's move this nitro over here. Okay. Now, instead of ortho, this is meta. It's got one carbon in between. Okay. And in this case, it would be 1-chloro, 3-nitro benzene would be the IUPAC name. If we put them exactly opposite one another, like this one, like that, then this would be parachloronitrobenzene. And the proper name then would be 1-chloro, 4-nitrobenzene. So meta is next door. No, let's see. Ortho's next door. Meta is one neighbor removed, and para is exactly opposite. Always 1-4. So it'd be 1-2 versus 1-3 versus 1-4.
And you wouldn't have to write out the whole word. You could just put O-M or P, right?
Right. With this convention, you don't have to say, but it only works for two substituents. If you got three, then you're stuck. But a lot of organic compounds, these benzene modified compounds, only have two substituents. Right? For instance, xylene. Xylene has two methyl groups. So if we put it here and here, that would be orthoxylene. But very often when you buy xylene, if you buy it at the hardware store, it'll say xylenes, which means it's a mixture of all three. So when you go in there and if you talk to one of the employees, you could confuse them by telling them, I only want orthoxylene. Do you have it? They say, what? What is that? They train them to run cash registers and find stuff on the shelf, but they don't teach them chemistry. Okay. If we find ourselves in need of the benzene ring as a substituent rather than a root, then this is the prefix that you would give it. If the benzene is connected directly to the root, then it's phenyl. It's phenyl something. If there's a carbon in between the benzene ring and the root, then it's benzyl, right? Or phenyl methyl. I like benzyl better. It's shorter. Both are proper. Now the question is, and the abbreviations are PH for phenyl and BN for benzyl. The question for me is, when is the benzene side group, when is it considered a substituent and not a root? That's what I want to know. So I'm thinking in these examples, in this first example, the root must contain the double bonded carbons. So that's why we would say 1, 2, 3, 4, 5, 6, 7. It would be heptene would be the root, or hept2ene for that first one. Oh, there it is. It's on the slide. And then the position where the phenyl group is, because there's no carbon in between it and the root, it's a phenyl. So we'd say 3-phenyl hep2ene. And the reason it's a side group, or a substituent and not the root, is because the root has the double bond in it. That takes precedence. I've never seen a convention that says, what do you do when you want to put both of them into the root? You don't do it. It just never happens. And the other ways are shorthand ways of expressing that. How about the bottom one? Well, that's a good question. Why don't we use benzene? Well, the reason we don't use benzene is because if we use benzene on one side and use the cyclohexane and the benzyl group on the other side, it would be a naming nightmare, for one thing. So we make cyclohexane the root, and then our benzyl groups are substituents. And that's a much more compact name. So position 1 and 4, which would be what? Para. 1,4-dibenzyl cyclohexane.